So as we were discussing the problem of spring back, right, that it returns to some degree, right, it returns to the previous, tries to return to the previous position, right, but it only relieves itself of the elastic energy, right, because the plastic energy is already has already been absorbed as dislocations, etc. So you see here during bending, the work is forced to take the radius RB, as it can be seen in the first image. And then include an angle AB dash after bending to punch in V bending, as you can see. After the punch is removed, the work springs back to the radius R and angle A dash. So RB has changed to R, and this angle has changed to, this AB dash angle has changed to A dash, right? So increase of angle here, and I'm sorry, decrease in the bend angle and increase in the bend radius. So that's what spring back is. So you have to take into account the spring back and change the final angle, isn't it? If the angle, if you want, is so and so, then considering spring back, you have to either increase or decrease that angle, the final angle, so that the final component would be as per our specifications and not, I mean, erroneous because of the spring back, right? So consider the error, or consider the issue here, that is spring back, so that you can have that taken into account, right? So that we can get the sheet, I mean, the required angle and the radius, etc., without failure of the sheet metal. Now, how do you get the bending force? The maximum bending force is estimated as follows. Here, F is the bending force. KBF times T into S into W into P square divided by D. Now, what is this? You have that KBF is your basically a factor. Depends on whether it is V bending or edge bending. So if it is V bending, you have the factor as 1.33. If it is edge bending, you have the factor as 0.33. So edge bending, you have a less of a factor here, and V bending more. Because in edge bending, you are trying to deform one side of the sheet, whereas in V bending, both sides would be deforming, right? So the force exerted would be more, and therefore KBF, the factor would be more, right? That's one explanation of it. TS is basically tensile strength. Those are not two different things. TS is the tensile strength of the sheet metal that is being worked upon by. W is the width in the direction of bend axis, as we have seen in those earlier examples. W is actually the width of the sheet, right? So that, and T is the thickness, square of the thickness taken into account, divided by D, right? Basically, it's the diameter of the what do you call the diameter, the bend, instead of the bend radius, you have the bend diameter, right? And if you can observe that, if you play with the equation here, try to understand what it's trying to tell us, that as we have discussed more, this factor, more would be the force required, or the maximum bending force required or induced, depends on how, depends on your perspective. So if that is the case, then tensile strength, more is the force required. More is the width, more the force required, as obvious. More is the thickness. You see here, thickness and the force relation is basically parabolic. So change of thickness would affect a lot on the force, right? And D is the bend radius, which is inversely proportional. More is the diameter of the bend, less would be the force required. Less is the diameter, more would be the force required, as simple, right? So the dimensions what they are saying, D is your this die opening dimension. V die and wiping die, as we know, this is V die, right? The workpiece would be placed here and then the curtain would come down. As for wiping die or edge bending, you have this sideways, I mean the punch moving down, right? All just beside the die. And it doesn't basically stop when it reaches the die because there is some gap kept. But here you would have to, the punch would have to stop at the die interface, right? Now, as for drawing, you see, before going to drawing, I think maybe it's a good time to have a look at that video, another video that I finalized. Sheet metal operations. Then you might be having drawing here in as well, but let's have a look at the different processes that it's trying to show 3D animation. So you see, with the help of that mallet, we are trying to bend it after holding it in place, trying to shape it. That's what we are trying to do. A flat piece into a punch is coming down, and therefore, as I was talking about, it takes the shape of the die, right? Pushes the circular brag to flow into the die cavity. This is how utensils are also made, right? It very resembles the household utensils we have. We have formation of this shallow cup shape. If you observe, tries to push that sheet into the die, right? Now, so punching. Now this is more of a press system here, right? Use arms, columns, etc. Trying to push that punch up and down. You can observe here. Punch moves down and shears the sheet metal. Punching is making a hole on the sheet by removing a slack. Right? You made a hole. Punching we already discussed, right? That's what is being highlighted again here. Blanking, we know if the useful part is blank, it's called blank. The remaining portion is the scrap. Right? Right? Depends on your perspective, what is the required component. Notching, this is another example of sheet metal operation. You see a partial hole is produced here. The edges of the sheet. Side shearing you can call. Another process called lancing. metal is sliced or split to free up metal without separating it from the original sheet. That's what we are doing lancing. Right? No metal is removed here, but there is a shearing action. It has removed some part of the sheet. You can save material and eliminate the need for expensive scrap removal systems because it stays in its place. Punch cuts the sheet partially and bends down. As you can observe, this is coining, another important topic in our syllabus. Coining, basically, we're trying to emboss a pattern, print a pattern, 3D pattern on components. Used to making coins and medals. If you have observed, how do you have that impressions on the coin? Kind of technique called coining, right? You see how that coining operation is taking place. Pressure required is also high, and the duration of force that is required is also high. Right? Embossing. Deforms the shape within the part, but without thinning of the part. Material is called embossing. See here. Tries to emboss text. Right. Here, this is very important when it comes to BIW kind of components, body in white. Without any thinning, you have that recess or projection, if you want to call it, right? So that's what is responsible for creation of that emboss, right? As we were calling it, embossing. You see shearing and bending. Let's have a look at those processes. We have already discussed these two, right? So it will be a good point to have when class.
A piece of metal is placed between the upper and lower dies and formed by means of the force and pressure exerted by lowering the ram. On brakes, the ram and upper dies. In a typical press brake bending operation, a piece of metal is placed between the upper and lower dies and formed by means of the force and pressure exerted by lowering the ram. On some press brakes, the ram and upper dies remain stationary, while the bed holding the lower dies provides the force that bends the part. 3 contact points are involved in a bend: the tip of the punch and 2 points on the female die. The material is bent to the desired angle as the punch enters the die. The larger the die opening, the smaller the force required to form a given angle. The principal terms used to describe bending on press brakes are bend allowance, bend angle, bend radius, and spring back. Bend allowance is the pre-bent length of material that must be included in a blank to allow for any deformation that occurs due to the bending operation. The bend angle is usually the included angle of the bent workpiece. It can also refer to the supplementary angle formed by the 2 bent tangent lines. The bend radius is a tangent line where the flat, straight section of the part stops and the radius of the bend begins. Springback is the tendency of the material to return to its original form. Springback typically ranges from 2 to 4 degrees.
Right, we've already discussed springback, right? The concept of springback. Doubts in today's class? If there are no doubts, then we can Okay then. We're done the meeting. Thank you.